Welcome students, welcome to the next session of structural analysis 2. So in the previous class itself, we have started our introduction regarding the stiffening girders. There we have analyzed a 3-hinge stiffening girder due to the application of some external point loads. Simply we are going into a brief introduction, then we are going into a numerical today's class also. So firstly, what is the main thing of a stiffening girder? In suspension cables, it is very important to maintain the parabolic shape. Okay, so that parabolic shape will differ due to the application of different loads. To maintain the parabolic shape, to consist or in order to maintain that thing, I am doing some extra arrangement to the deck. So that is nothing but the application of the to satisfy keeping that shape. Okay, so as the cable with the parabola shape is uniform should be there in the suspension type bridges. That is the condition in the suspension bridges. When this shape comes, when I am applying the UDL. When I can apply the UDL due to the application of some point loads are also happening. So when we indicate or add the stiffening girder, this stiffening girder or a simply supported type of beam structure is converting the applied point loads into the form of uniformly distributed loads along the vertical suspender to the cable. So the main form or the main condition in the suspension cable is the main cable should be in the parabolic shape. That parabolic shape only comes when the load on the cable is uniformly distributed. How we are applying the uniformly distributed load? When a vehicle is having some moving type or a point loads, it will cause funicular shape, but I want to convert it into UDL. That's why we are indicating stiffening girders. That stiffening girders are converting these point loads and causing that into the UDL, and this UDL is being transferred to the nearly or closely spaced vertical suspenders. Okay, so the external loads are carried by two main 3-hinge or 2-hinge. So whatever it is. Okay, girders. While the girders are supported not only at the ends but also through the vertical suspenders or the very closely spaced hangers. This will connected to the cable and that loads will be transferred as the UDLs. Okay. So this is the overall structure, a simply supported girder or a simple girder and the main cable, vertical suspended indication, and this is having two point load application, and due to this point load there is a generation of WE intensity. WE is the intensity of the UDL that is being transferred to the cable. So due to this action, this cable is having only WE acting downwards. Some UDL is acting downwards on the cable, but this down portion, there is this girder is there. This girder is experiencing external loads and also this girder is experiencing upward UDL. Okay. So when I observe this individual equilibrium condition we have mentioned, so this UDL is only having, this cable is only having the UDL in the downward direction, but this girder is having downward external loading condition and also upward UDL condition. Okay, so this is the individual equilibrium of the structure. And then individually considering the cable structure. So as we have already said, when the loading is UDL, the shape will be a parabola. So as our load is WE UDL, the shape of the parabola is the y is equal to 4hx by L square into L minus x. There the vertical reaction in the support only when we observe the top segment, only the cable equilibrium consideration when WE is the UDL acting on the cable. Now WE into L by 2 and H is equal to WE L square by 8H, and due to these two, tension at the supports are the maximum tension is equal to under root V square plus H square. These conditions already we have discussed. And then for the girder, again in this girder we have said application of two loading conditions. One is the upward UDL. So first one is the external load. Second loading is the upward UDL. So these two I am indicating. And after that we are considering a section. What we need to do, as we have already said, this girder is acting like a beam. So for the beam simply supported like girder, we should have to generate shear force and bending moment diagrams. So for that we need to calculate what is the actual shear force at the section, what is the actual bending moment on the girder at the section. So this is the condition where we are considering a section line, and where capital M, the actual bending moment in the girder is equal to capital M suffix x minus hy. So M suffix x is M suffix x is indicating the beam moment in the girder, and that h into y is indicating the h moment. How I can calculate bending mx? Mx will be generated from this portion. Mx will be generated from this loading condition. Loading 1 will give the answer of mx. H moment will be calculated h into y. As we know, at that particular y point, what is the y answer? So, at this section x in the cable, what is the y dip? So, that y we are multiplying. So, h into y. In this way, the capital M beam moment minus h moment will be calculated. So, bending moment at any section on the girder. So, the actual bending moment at any section on the girder is the whole formula. If we want any position, that position we will calculate y, and the structure's capital H, and that position's original beam moment we will calculate. That position's original beam moment, that position's y answer, and capital H of the cable. So, involving these three only, actual bending moment in the girder will come. But we said this is a 3-hinge stiffening girder. I can say at that point C, when in the beam MC I know. So, when we consider the simply supported type beam and giving the application of external loads, maybe at the point C, I can calculate bending moment at C, but I will indicate as beam moment C. Okay, beam moment at C minus h into y. So, that should be equal to beam moment at C minus h into y at C. So, using those two values, we will get actual bending moment in the girder at C. So, when we involve these two answers, it will give the actual bending moment in the girder at C. But in the actual case, bending moment in the girder at C is 0 because there is a hinge. That's why we have got the final output as capital H is equal to MC by H. So, capital H, the horizontal component of reaction, is equal to MC by H. And then using that H, using the basic formula capital HE, when the UDL application, H is equal to WE L square by 8H. In this way, I can calculate WE. What is the UDL acting on the cable which is causing this H? Okay. Now, using that WE, I can calculate V, vertical component of reaction, WE into L by 2. Using this H and V, I can calculate the maximum tension. In this way, from the first step itself, we are calculating capital H, capital WE and capital V, and also the maximum tension on the cable. Now, considering the actual shear force, like the same thing here also, this shear also involves two parts. One is shear or the beam shear, okay, beam shear of the simply supported girder, and also minus h tan theta. The derivation of this part we have already concluded in the previous session, okay. So, Sx minus h tan theta. So, Sx is indicating the beam shear in the simply supported girder due to the application of external loads, okay, due to the application of external loads. What is the beam shear at that section, that is Sx, and h and tan theta, the corresponding points slope, okay. So, h value, and where the point we are calculating this consideration, where the point we are calculating the shear, at that point that there will be a slope in the cable, right? So, that slope in the cable will be tan theta. In this way, we can calculate S is equal to Sx minus h tan theta, M is equal to Mx minus hy. You need to remember these two formulas only. Actual bending moment in the girder is equal to Mx minus h into y, and actual shearing force in the stiffening girder is equal to Sx minus h times tan theta. Now, what is this Sx and Mx? These are the shear and moment for the beam girder or this simply supported beam girder when the external load is applied. Shear when external load applied, moment when external load applied at that particular section. Why? We already know the corresponding dip of the position. Tan theta is slope of the particular point where we are calculating these moments or shears. Okay. So, these two are the main outputs for calculating moments and shears. As we know, individual moment answers, individual shear answers. Can we develop bending moment diagram and shear force diagram? Yes, we can develop bending moment diagram and shear force diagram. Okay. So now I am going into a numerical which is having a 3-hinged stiffening girder. Okay, the 3-hinge stiffening girder of a suspension bridge of span 120 meters is subjected to 2-point loads 240 kN and 300 kN at a distances of 250 meter and 80 meters from the left end. Okay, so see here, when they are mentioning a cable with 2-point loads, that is the first condition. Startingly we have given cable structure with 2-point load application, so we have analyzed that part. But in the problem itself, in the first line itself, they are saying it is a suspension bridge type and having stiffening girder, and that suspension bridge is carrying 2 loads. Those are these values and which are being located at these positions. Okay, and we need to calculate the shearing force and bending moment for the girder. So SF and BM for the girder at a distance of 40 meters from the left end, as the complete length is 120 meters. At the 40 meters from the left end, I need to calculate shear force and bending moment of the girder. And the supporting cable has a central lip. They have given some other data. The supporting central main cable. Okay, the main suspension cable is having a central lip of 12 meters. So we should have to calculate tension in the cable. Okay, we need to calculate the tension in the cable and also draw the bending moment diagram for the stiffening girder. Okay, so these are the final conditions we need to evaluate. So what it is saying? So we are having a cable and we are having a stiffening girder arrangement with 3 hinges. So as they have mentioned 3 hinges, I am indicating with the dots. Okay, and maybe if you want you can indicate for the supports A, B, and C. And this having the complete span as 120 meters as given in the problem. And also it is having a central dip of 12 meters. And this stiffening girder or this complete suspension cable bridge is carrying only like a support indication. I am giving with a hard stratum type indication. Level we will indicate, right? So that we are indicating, and there is an application of 2 pointers, 240 kN and 300 kN, which are acting at 25 meters. So 240 kN and also 300 kN at 80 meters. So this one is 25 meter distance and that one is at 80 meters from the left support. So in this way the structure may appear. For this structure I need to calculate shear force and bending moment of the stiffening girder at 40 meters from the left end, and also I need to calculate tension in the cable, and also we need to draw the bending moment diagram or the actual bending moment diagram for the girder. Okay, when we observe the picture clearly, this may look like this. See, the support A and the support B were like that, and we are having a 3-hinge stiffening girder with ferrule hinge at C point, and we are having the cable with A, B and C. For the indication at this C only we have indicated C, so that I can indicate the dip value. Small h is equal to 12 meter and the complete span as 120 meters, and there is a point load application of 240 kN and 24 meters. Later with some 55 meter distance, because it is 80 meter from the left support. This is 300 kN. As it is completely 80 meters, the remaining 40 meters is there. So the complete remaining distance from that support is 40 meters. So in this way the given loading condition was completed. So what we have said till now, so this is our loading condition, as I need to calculate a capital T, tension in the cable, and also I need to calculate moments and shearing forces in the girder. Firstly, I am thinking about tension calculation. Okay, so tension in the cable will come as it is involving under root V square plus H square. Yes, under root V square plus H square. So for calculating tension, these two answers needed. Now, what is V? WE L by 2. What is H? WE L square by 8H. So, for getting these two answers, I need these two. Nothing but WE answer I needed. And for calculating this capital H, I have one more condition. What is that condition? MC divided by small h is equal to capital H. MC divided by small h is equal to capital H. This is the condition we have already generated. At the third hinge, at the 3-hinge stiffening girder, at the third hinge, in actual condition, the bending moment is equal to 0. From that condition, we have got this point where that capital M suffix C is the beam moment at C due to the application of external loads. So, A, it is B, and at C, and this is the actual loading figure on the stiffening girder. So, due to the application of the external loads, what is the moment at C? That answer is MC. Due to the application of external loads, at the time C is just a point. Later, we are going into C is a hinge. Okay. Here I am going in the condition that C is a hinge. Initially, it was simply a beam, and at C I am calculating the beam moment. Nothing but the bending moment at C value. Okay. So, this MC will be useful here, and small h is tip of the cable. Using these two answers, I can calculate capital H. Again, by knowing the capital H answer, I can calculate WE. Knowing the WE answer, I can calculate capital V. Knowing the capital V and capital H, I can calculate tension in the cable. So, in this way, the portion will be involved for calculating the tension in the cable. Okay. Now, go into the problem. Firstly, considering the stiffening girder as a simply supported beam supporting the given external loads, what we have said for calculation? We need to calculate MC answer. We need to calculate H answer, small h answer. Okay, that is MC, how it will come? Taking this girder as a simply supported beam being subjected to the external loads. Then I can calculate at C what is the bending moment. Okay. So, considering the stiffening girder as a simply supported beam supporting the given external loading conditions. So, this is our structure with two simply supported ends, and the C point is nothing but 3-hinged girder, means C is at center only. Okay. Maybe at some other condition, some other position they have not mentioned. Here 3-hinged girder is there. So, this 3-hinged stiffening girder, C point or the hinge point is at center only. So, that C location is, I have indicated as 60 this way, 60 that way. Now, bending moment at C for this picture only. Bending moment for this picture, MC. How we will calculate? For calculating this type of simply supported beams, I need to calculate the support reactions at A and B. So, for calculating bending moment at C, which is nothing but M suffix C. What is this MC? Because this MC is only giving me the answer of capital H. This capital H is only giving me the answer of WE. This WE only gives me the answer of V. This V and H combinedly will give me the answer of capital T. So, involving all these steps, firstly I am concentrating on capital M suffix C. So, for calculating the tension in the cable, I need to calculate bending moment in this stiffening girder while considering it as a simply supported beam. Now, for this simply supported beam, for calculating bending moment at any point, we need to calculate the support reactions VA and VB for the stiffening girder. VA and VB for the stiffening girder only. Okay. So, support reactions for the girder with the external loading system is equal to, due to the vertical equilibrium condition, VA plus VB. What are the forces upward? So, VA and VB. Downward forces 240 plus 300. 240 plus 300 kilonewtons, which we have got as 540 kilonewtons. And then summation of all the moments about A, sum of all the clockwise moments is equal to anti-clockwise moments. So, VB into 120, as it is the 120 length, just now we have said, and 240 into 25 is equal to 240 into 25 plus we are having another clockwise force, that is 300, which is located at 80 meters. 300 into 80 meters from the left support. Summation of all the moments about support A. So anti-clockwise moment VB into 120 is equal to 2 forces along perpendicular distance. So in this way we have got vertical component of reaction at support B due to the application of external loads on the girder. So these are the support reactions at B. And then from the top reaction I am calculating VA. So VA and VB calculation was over. After calculating the support reactions, what we can do? I can go to the calculation of bending moment at the point C. So before entering into bending moment at point C, I am calculating remaining two answers also. So due to the application of the external loadings, these are the original loading condition, and we have got 250 and 290. Sorry. These are 240 and 300, I think. 240 and 300. So this is the original loading figure we have got. So for this original loading figure, I need to calculate bending moment at this C location, which is at a distance of 60 meters from A. Okay, so this is the output I need to calculate. And in the problem, what I can do, at the remaining points also I am calculating the bending moment. So the first thing, bending moment under the load of 240 kilonewton. So bending moment under the load 240 kilonewton. What it is involving? Only the left side VA answer. So VA into perpendicular distance. 290 into the corresponding perpendicular distance is 25. Because under this point load means it will not involve this force. So force into perpendicular distance up to the point only it is involving. If you want to write 240 into 0. Okay. So 240 into 0 is nothing. So 290 into 25, the output we have got as 7250 kilonewton meter at this point. And at this second point, bending moment at this section, either in this way we can get or in this way also we can get. When we go with 250 into 40. So when we go like this, 250 into 40 is the sagging type moment, that is the bending moment at point load of 300. Or if you are considering in this way, see here, 290 into 80 plus, minus 240 into 55. So either 290 into 80 minus 240 into 55. So this segment's force moment, or only this forces 250 into 40 perpendicular distance. So that is also the bending moment at the second loading point, which is a 300 kilonewton load. So bending moment under the 300 kilonewton load I am calculating. Why these two I am calculating? Because easily I can develop the bending moment diagram for the girder with the external loads. Okay. And then bending moment at the point C. Where it is located? It is being located at 60 meters from A. Now bending moment at this position is equal to 290 into 60 and minus 240 into 60 minus 25. So force into perpendicular distance. Force into perpendicular distance. In this way I have calculated bending moment at C, which is equal to 9000 kilonewton meter. Now connecting all these points, I can develop bending moment diagram for the external loadings. So this is the bending moment diagram for the girder only with the external loading conditions. When I am connecting, I can simply say bending moment at A, bending moment at B will be 0 as they are the simply supported edges. So from 0, and the next projection line I have got 7250, and then the next point load location of 300 kilonewton, we have what? 10,000 as the answer. Connecting all this, a single degree straight line equation, because it is force into perpendicular distance, force into perpendicular distance. Single degree power we have got. So these are the answers there we have mentioned. And at that intermediate point or at the center hinge point, we have got the bending moment as 9,000 kilonewton meter. This is the picture of the bending moment diagram, that is beam moment diagram. We have given m suffix x, right? So this m suffix x answers are coming from this equation only. So m suffix x beam moment diagram. This is not the actual bending moment diagram for the stiffening girder. This is only due to the application of external loads, because the girder is also having UDL. Okay. Now, as we have already mentioned, the calculation of the horizontal component of reaction capital H is equal to MC by H. Just now we have calculated MC as a 9,000 and central dip of the cable is 12 meters. So we have got 750 kilonewtons. And from H, using the horizontal component formula WE L square by 8H, WE is the unknown and the corresponding L is span of the cable, H is central dip of the cable. Substituting all these things and using the H answer here, I have calculated UDL of 5 kilonewton per meter. So what it means, due to the application of 240 kilonewton and 300 kilonewton on the girder, it is transferring the load into the form of UDL with an intensity of 5 kilonewton per meter in the upward direction. Okay, so on the girder, I can observe 5 kilonewton per meter upward UDL and the application of 2-point loads. So this is the original condition of the girder. So these loads are being converted as the UDL. Now this cable is having a UDL of 5 kilonewton per meter only. So only the cable structure is having a UDL of 5 kilonewton per meter. Now when we know the load on the cable, can we calculate the vertical component of reaction S? If it is a 5 kilonewton per meter, half of the total load will be given as this, half of the remaining load will be given as this. So 5 into length of the cable, length of this span divided by 2. Then the vertical reaction of the cable is equal to WE into L divided by 2. So we have got 5 into 120 divided by 2 in the answer. The vertical component of reaction is 300 kilonewtons. And in the problem they are asking us to calculate the tension in the cable. So the maximum tension in the cable T max. So they have not at all mentioned at a particular point calculate tension. Only I am calculating at the support A or at the support B point. What is it T? This T will be TA is equal to TV is equal to under root V square plus H square, because at the two supports the vertical component and horizontal component will be equal. Why it is equal? As I am giving the symmetrical uniformly distributed load. So the substitution of capital V, just now we have got as 300 km and capital H in the previous step only I have got it as 750 kilonewtons. Using these two answers, I have calculated maximum tension in the cable. So in this way, calculation of maximum tension only completed. And then we need to go for calculation of actual bending moment in the girder at a point, actual shear force at a point. So the next thing is actual shear force for the girder at 40 meters from the left support. So what is the original formula? Original formula for calculating actual shear force on the girder is equal to S is equal to Sx minus H into tan theta, where this S suffix x is indicating beam shear. Beam shear means only we are considering this girder with point loads. So only with this action, only with this loading application, what is the shear force we have got at the point where we said 40 meters. So at this 40 meters, what is the shear force for this girder is the beam shear. Okay, so this answer is Sx, and capital H is horizontal component of reaction, we already know, and then tan theta. Theta is involving the slope of the cable at this particular 40 meter position. So as the cable is having the curve shape, each individual point will have different inclinations, right? So at the position of 40 meter from the left end, what is the inclination, the corresponding tan theta I need to involve. So I need to calculate Sx, I need to calculate tan theta, and I need to substitute capital H. So finally we will calculate capital S at the location of 40 meters from the left support. Now I am taking the corresponding loading figure for calculation of S suffix x. So beam shear at 40 meters from the left support is equal to VA as it is involving this 240 kilonewton point load also. I need to say 240 remove. Left side upward positive shear force, left side downward negative shear force. So minus 240 and plus VA. So in the previous step itself we have calculated capital B, VA, which is for the girder. VB and VA we have got as 290 kilonewton as the support reaction of the girder. So 290 minus 240, which we got, plus 50 kilonewton as the positive shear force occurring on the beam girder. See here VA and VB. This case, what is the support reaction, not the original beam. For this girder, what is the support reaction that I am involving? Okay. And then tan theta. For tan theta, I need to use the parabolic shape of the cable. So y is equal to 4hx by L square into L minus x. And with the differentiation, we have got dy by dx, which is equal to tan theta. And with the differentiation, I have given as 4h by L square into Lx minus x square multiplication. So with the coefficient L, with the x square, we have got 2x. So this is our answer. What it will give? Which position you want to calculate the slope, that positions x I need to substitute in this. When we substitute x answer, the corresponding dy by dx will come. So as I need to calculate x at 40 meters. So substituting x as 40 meters, central tip of the cable as 12 meters and span as 120 meters. After substituting all these things, I have got the tan theta answer as 0.133. No need of converting it into angles because I need tan theta value as it is. Now we have calculated Sx answer, we have calculated tan theta answer, and we can go for the substitution. So Sx minus h times tan theta. So Sx, how much we have got? Plus 50 kilonewtons. 50 kilonewton. And the horizontal component, how much we have got in the previous step? Even in the tension also we have given, right? So that capital H is 750 into 0.133. So with this multiplication, finally we have got the actual shear force on the girder as S is equal to minus 49.75 kilonewton. The only thing you need to remember here is where I am using the response of the beam type or where we are using the original structure. So in this way we can calculate the actual shearing force on the girder. In the next class we will go into the calculation of actual bending moment and we will generate the bending moment diagram for the 3 hinged girder also.